Going on to topic 3 now of chapter 11, we're dealing with conditional probability and events involving and. You'll remember N was a conjunction and intersection of events or elements. So what is conditional probability? Well, we'll just look at this. Sometimes the probability of an event must be computed using the knowledge that some other event has happened, or is happening, or will happen in the future. The timing is not important. This type of probability is called conditional probability. And the rule, the probability of event B computed on the assumption that event A, this is some other event that's going to happen or will happen, is called conditional probability of B given A, and is denoted conditional probability of B given event A. All right, let's go on to our first example. Select from a set of numbers. Now our sample space will be the first 10 whole numbers. We want to have a single number is to be selected randomly. Find each probability given the event. Now for set A, the selection or the selected number is odd, and then B, the selected number is a multiple of 3. So as we look at this, so from our sample space, we want to select the odd numbers. So that would be 1, 3, 5, 7, 9. And then conditionally, we want to select a number that is a multiple of 3. So from our sample space, that would be 3, 6, 9. So this is an and, an intersection. And what do we find intersecting? Well, we have a 2, a 3, and a 3, and a 9 and a 9. So in a sense, 2 elements. 2 elements out of 10 meet our criteria, which we can reduce to 1/5. And if we look at the work that is shown in the solution area, our set B, as we said, were 3, so 3 out of 10, and set A we had defined as these. So we're looking for intersection. We got the 3 and the 9, and then putting it into the more formal formula, we get 2 out of 10 or 1 out of 5. So as we look at example C then, in the given condition that A occurs, that effectively reduces the sample space of all 10 numbers to just the odd. That would be 5. And then the elements of the new space that are A and also B are reduced by the intersection of A and B. So we said that was 2. And now A is our new sample space of 5, so we get 2/5. So in looking at what we got there on the previous slide, which was this, actually comes from this. And notice that our sample space was 10 here. So if we multiplied each part of this complex fraction by 10, or numerator and denominator by 10, here the denominators just cancel out, and we get the 2/5, which is what our answer was. So a derivation of this to this is proved by this. So in a sense, you're multiplying both of these fractions by your sample space, n parentheses s. So these cancel out, and you are just left with the numerators of both parts. Okay, again, you have the formula. You don't need to work with this. So the conditional probability formula, notice this is the symbol for intersection, and we're replacing the intersection symbol with the word and. So A and B, or A intersecting with B, over your sample area. We're going to give a second example now. So a second observation from example A is that the conditional probability of B given A was 2/5, whereas the unconditional probability of B with no conditions given was 3/10. So that you did have the condition did make a difference. Let's go on to example 2. Here we're going to look at finding probabilities of boys and girls in a family. Given a family has 2 children, find the probability of each event. A, both are girls, given that at least one is a girl, and then B, both are girls, given that the older child is a girl. And we're assuming that the events boys or girls are equally likely. So let's do some definitions. So looking at our sample space, S, you could have 2 boys, a boy and a girl, or 2 girls. Now we're looking at both are girls. Out of the 4 possibilities, that is 1/4. That at least one is a girl, as we look through here, so that's 3 out of 4, and that the older one is a girl, that is, let's say the G and the GB is 2 out of 4. Okay. Note that A intersecting with B, where both are the same, is this. And if we reverse it, A, or look at it, A intersecting with C, that is the same. Thus, A intersecting with B is the same as A intersecting with C, which is 1/4. So using our conditional formula, which is the probability of A given B. We have this, and we said this was 1/4 and this was 3/4. Now in these fractions, another way of doing it, the way the author was showing earlier, we just multiply both of these by the common denominator here of our complex fractions, and these just cancel out. So we get 1/3, which is what we have here. Now in dealing with item B, where the probability of A given C, which is again 1/4 divided by now 2/4. Again, the 4's are just going to cancel out, and you're left with 1/2, whichever way you do the computation. Going on to independent events, sometimes a conditional probability is no different from the corresponding unconditional probability. If this is true, we say the two events are independent. So it doesn't make any difference whether they're conditional or not. So the rule being two events, A and B, are independent events if knowledge about the occurrence of one of them has no effect on the probability of the other one occurring. A and B are independent if the probability of B given A is equal to the probability of B all by itself, or equivalently, given the probability of A given B, which is equal to A all by itself. So let's take a look at an example, because this gets a little bit wordy. So in example C, checking events for independence. A single card is to be drawn from a standard 52 card deck. So the sample space is 52 elements. Find each of the following given the events. A, the selected card is a face card. And B, the selected card is black. Well, we'll define our black area first. And here we see there are 26 black cards in a 52 card deck. So if we set up our ratio, 26 out of 52 equals 1/2. Now we are going to check conditional probability, where face cards. Now in a 52 card deck there are 12 face cards and 6 of them are black. So we get 6 out of 52, and there are 12 face cards out of 52. So this gives us, again, the 52s are going to cancel out. This gives us 6 over 12, which is 1/2, as we see there. Now, because the first part of this was 1/2, and the second part is 1/2, we refer to these events as being independent. because the ratios are the same. I like the way the textbook goes back into previously discussed material and brings it sort of up to date. Here we're looking at a Venn diagram where S is our sample space, set A, set B, and the area of intersection is this colored area in the middle. So we describe this perhaps as the probability of A and B, and again the word "and" indicating intersection can be described as the probability of A times, that is the product of the probability of B given A. And this is what they describe here. So they are independent events when A and B, again, are independent. And we'll do some multiplication, as you'll see later. As we go on to example 4, selecting from a set of books. Here this person has a collection of books, and there's 20 in all. She has some that are fiction, non-fiction, and then hardcovered, paperback. And here is the summary of what she has. So let's take this item by item. If Jackie randomly chooses one of these 20 books, find the probability that it will be each of the following. Hardcover. Well, how many hardcovered books do you have? 8. What is your sample space? 20. So this one's easy. 8 out of 20 reduces to 2 out of 5. All right, part B. It's fiction given it is hardcovered. Well, now in this case you are reducing your sample space because you're saying you are picking something out of a hardcover. So 3 fictions out of 8 hardcovers. So that gives you the ratio 3 out of 8. But now you're expanding your sample space to include, for letter C, hardcover and fiction. So in letter C, hardcover and fiction, so we can use our results here, 2/5, and this is multiplication, times 3/8. But notice we can do a little cross-canceling here. 2 will go into there once, 2 will go into there 4 times. So now we end up with 3 out of 20 as our probability. And here they're saying this verifies the general multiplication, that out of your total collection of 20, there are 3 hardcovers that are fiction, which is what we got. In example 5, we're going to select from a set of planets. And here nicely the planets, I see that Pluto is no longer mentioned. That's a sub something or other. All right, let's take a look at this now. It says find the probability that the first one selected is closer to the Sun than Mars. So that's our first choice here. So here's Mars. So Earth, Venus, and Mercury are closer than Mars. So this would be 3 out of 8, which is what we get right here. And the second is closer to the Sun than Saturn. Well, we go to Saturn here now. And there are 1, 2, 3, 4, 5. But we already have eliminated Mars. So we just have 4. 1, 2, 3, 4. And there's one less to choose from. So this is going to be 4 out of 7. So let's do our multiplication. And before that, the one that we are eliminating is either Earth, Venus, or Mercury that we've selected, not Mars. So that still gives us 4 out of 7. So we do our, again, cross multiplication, where we can cancel a 4 out of there once, 4 out of there twice. So that'll give us 3/14, that when we put it into decimal form gives us this. So again, lots of stuff that we've done in the past are being brought in so that we can do our calculations and some logic and analysis of what's going on. And just reflecting on 5 for a moment, in the condition that A occurred, change the probability of B, since once you selected one of the planets, Mercury, Venus, or Earth, without replacement, you've picked that one. So that one, you took it out of the possible selection. So repetitions were not allowed. So events A and B were not independent. On the other hand, in our next example, example 6, we're going to see that A and B are independent. All right. And having your textbook gives you these nice colored diagrams here. So again, Carrie must select 2 planets, but this time one is for an oral report and the other is for a written report, and they need not, here's the key, be distinct. Here the same planets may be selected for both reports. So again, find the probability that if she selects randomly, the first will be closer than Mars, and the second closer than Saturn. So here our events for A were 3 out of 8, but now you don't eliminate the one you've chose, and it will be the second 5 out of 8. So here nothing will cross cancel, and we get 15 out of 64. That gives us this approximation. And again, repetitions are allowed. All right, in example 7, selecting again card from a deck. 52 cards. Let B denote the events that the card is black. Let D denote that the event is a diamond. Are set B, in a sense, and set D independent? And later, are they mutually exclusive? So here, again, knowing about decks of cards are critical. For D, how many cards are, let's say, diamonds? Well, that's one suit, and that would be 13 out of 52, which is 1/4. And how many diamonds are black? Well, the diamonds by definition are red. So that's going to be 0 out of 26. And they're saying since the conditional probability of D given B is different from the unconditional probability of D, then B and D are not independent. And mutually exclusive events that cannot both occur for a given performance of an experiment, since no card in the deck is both black and a diamond, B and D are mutually exclusive. In example 8, Anne is still drawing balls from an urn, as shown at the side. This time she draws 3 balls without replacement. Find the probability that she gets a red, a yellow, and a blue ball in that order. So, here you have to count how many are red. Well, there are 4 reds, 5 yellows, and 2 blue. So a total of 11 balls. So on her first choice, as she digs in there, the probability that she's going to get a red is 4 out of 11. Now, there were 5 yellow, but now 1 ball has been taken out. So the probability that she would get a yellow would be 5 out of, again, 1 less ball, 10. And there were 2 blues, but now 2 balls have been taken out, would be 2 out of 9. And notice this, you can do some kind of division here. This would be like 1/2 here. So then the 2's would cancel out there as well. So this would give you 4 out of 99. I probably should have written that out. But again, this would be the decimal indicating that given the order and the not replacing the balls give you this probability. In example 9, selecting from a deck of cards. If 5 cards are drawn without replacement, this is similar to what we did earlier in selecting the balls, from a standard 52 card deck, find the possibility that they are all hearts. Well, in your first choice, you get 13 out of 52. Now that one has been selected, there's 1 fewer card in the deck. There would be 12 out of 51. Again, 2 fewer cards, 11 out of 50, 10 out of 49, 9 out of 48. And since you're using your calculator, there are places where you can cross-cancel a little bit, but eventually they ended up with this, which is this. Quite a small number. Now they're also indicating here that throughout, other formulas may have been able to be used when you're doing this. You could have solved it as a result of combinations, 52 with 5 selected out of that, and then using this, and there is your permutation there, and they show the answers come out the same. Perhaps this way looks a little easier at this stage. In example 10, we're going to use both addition and multiplication rules. Here, 2 local garage employees, 2 mechanics, Ray and Tom. By the way, I don't know if you recognize these fellas. They are Click and Clack, the Tappet brothers. On public radio for many years, they had Car Talk. They're both MIT graduates, so they're actually engineers, but they did have car repair, and of course they're just making something up here. It says, your consumer club has found that Ray does twice as many jobs as Tom. Ray does a good job 3 out of 4 times, and Tom does a good job only 2 out of 5 times. That wouldn't be true, but that's what they're saying. If you plan to take your car in for repairs, find the probability that a good job will be done. Okay, we'll raise this up and analyze it. So as we start to analyze this, we'll let R equal work done by Ray, and T work done by Tom, and G for the good job done. Since Ray does twice as many jobs as Tom, the unconditional probabilities of events R and T are respectively 2 out of 3 and 1 out of 3. Because Ray does a good job 3 out of 4 times, the probability of a good job given by that Ray did the work is 3 out of 4. And because Tom does well 2 out of 5 times, the probability of a good job given by that Tom did the work is 2 out of 5. These last 2 probabilities are conditional. These 4 values can be summarized then as Ray doing a good job, Tom doing a good job, and as we see this, given R, which is Ray, given Tom, which is T. Event G can occur in 2 mutually exclusive ways. Ray could do the job and do a good job where they intersect. Or Tom can do the work and do a good job, again, where these intersect. Remember, G is the good job. So we then have the sum of this, which is the product of these plus the product of those. And pulling all this information in, we get this. And then when we do our cross-canceling, and the math is not that difficult, here our 3's will cancel out, 2's will cancel out there. So this leaves me with 1/2 plus 2/15. And if we want to add these together, we have to have a common denominator of 30. So 2 times what is 30? 15. So this is 15 here. And 2 times what? Or 15 times what is 32? So this is a 4. So there's where we get our 19/30ths. And in decimal form is this. So that's not too bad. You're probably going to get a good job because that's greater than half. In the tree diagram that we see here, it's another way to show the example 10 that we just finished, where there's Ray and there's Tom and there's the good jobs. Remember, G complement was not the good job. So when we added all of this up, they're saying the sum is what we got, 19/30. Okay, in selecting a door prize, Rob is among 5 door prize winners at a party. The 5 winners are asked to choose without looking from a bag, so they're going to reach into a bag to pull out a token. Now there are 5 tokens. 4 of them give you candy canes, but one of them is a $100 gift certificate. Can Rob improve his chances of getting the gift certificate by drawing first among the 5 people? So they set it up, and drawing the gift certificate is 1 out of 5. And then the second person is 1 out of 4. The third person is 1 out of 3. Again, we're not replacing, and so on and so forth. And here, initially, it's 1 out of 5. But then when you do the multiplication here, you get 1 out of 5. And do the multiplication here. Notice everything's canceling out, and you still get 1 out of 5. So the answer then, the order in which the 5 winners draw, does not affect Rob's chances. It's equal chance as you go through. But of course, once the gift certificate is drawn, then in a sense the others don't have a chance at all. But we're assuming if it isn't selected. Okay, then we have some exercises here. We'll play around with these a little bit if we have time. And again, just under 40 minutes.